Hi everyone. So this lesson is about latent heat. This is one of the last lessons for the semester. Kind of sad, I know. Okay, so we talked about latent heat indirectly and we didn't mention it explicitly when we had this entrance ticket, the warm-up, I'm sorry. I think it was last week. So we discussed what was the most effective way to cool a warm Dr. Pepper if 25 grams of water at 0 degrees or 25 grams of ice at 0 degrees. And practicality aside, and the fact that no one really would say, hey, would you like some cold or super cool water on your drink? That aside, we said that ice would be the best choice because it had to undergo a phase change. What that means is the ice would go from solid to liquid, right? So just the ice would melt. And that's where we stopped, because then we talked about specific heat. Now we're going to go back to this to see, okay, so what's the physics behind the reason ice is better than water, even if they're at the same temperature. Okay, so I'm going to read this from the text and just explain a little bit what that means. This says energy is required to melt a solid because the cohesive bonds between the molecules in the solid must be broken apart such that in the liquid the molecules can move around at comparable kinetic energies. What this is saying, before I talk about this next part, is that to melt ice you need energy, right? Energy has to come from somewhere. And the reason why is the molecules in a solid, in this case ice, are close together, tight, right, in a very ordered manner. Look at the arrangement over here. So you need energy to break these bonds and have the molecules move a bit more freely. We want a similar kinetic energy between the ice, well, in this case, with the water around it, and the air around the icicle. So that's what's happening. You need energy, right? So that the water here, as the icicle melts, has a similar in value kinetic energy as the air around it. Now, the energy, where is it coming from? Well, from the air around it. Because remember, it's trying to reach thermal equilibrium. So it's getting that energy. Now, and then something I want to point out is we can think of the process in reverse. So now let's talk about again solid and liquid. So you need energy input, meaning you need energy from somewhere. Now, if you're doing the opposite, going from liquid to solid, we call that freezing, then you need, well, not you need, but you're going to have an energy output. That means it's going to release energy. This will make a bit more sense when we define endothermic and exothermic reactions, but for now, just try to remember that. And today we're going to focus a bit more on the fact that to go from solid to liquid, you need energy from somewhere. Okay, so that's solid and liquid. What about gas? We're going to focus on those three phases or states of matter. Well, if we want to make water vapor, then we also need energy. So again, I'm going to read and explain a bit more. Oh, and I skipped this part. No rise in temperature, but again, I can do the same over here. Meaning, when I explain it, it will apply for both situations. It says, similarly, energy is needed to vaporize a liquid because molecules in a liquid interact with each other via attractive forces. Now, again, so same thing, very similar to the solid, even though they're moving a bit more, not a bit more, but I guess they're not as tight, the molecules as close together as in a liquid. But when you add more energy, you have that energy input. But now the particles, as you increase the kinetic energy, they need more room, they're moving faster. So that's how you get water vapor. Now, What if we do the opposite, where we make the gas into a liquid? That's called condensation. Well, that releases energy. So they're very similar. Now, and it says there's no temperature change until a phase change is complete, meaning until all the liquid has become gas, or until you get gas, then you're going to have a change in temperature. And then this is the same over here. Until all the ice has melted, meaning it's become water, then you're going to have a change in temperature. So if we were to focus, let's say we had a thermometer only focusing on the ice right here at this part, let's assume it's at 0 degrees Celsius. It'll reach 0 degrees Celsius until it's become water, then we're going to have a change in temperature. Okay, but there's no temperature change. Now it's not talking about the system as a whole, but just this part, which is the ice. That's why he's saying energy is required to melt a solid. So the solid will not, as long as it's a solid, right, even though it's melting, will reach 0 degrees until we have all of it become water. And then over here, the water will be, let's say, at 100 degrees Celsius until it's all become water vapor. That's why it burns, because it could be at a higher temperature than 100 degrees Celsius, water vapor. Now, let's focus on this. Energy is needed. Then energy is required. Okay, that is the latent heat. That's what it means. Latent heat is the energy required to undergo a change of phase. Now, latent, that also means kind of like hidden. And I think that's very interesting because, and very appropriate. Because then if you were only focusing on the temperature and we wanted to describe energy, only in this case, this type of systems, when you have a change in temperature, well, there's no other way to describe a change of phase because, meaning without latent heat, because you'll have, let's say for ice still be at 0 degrees, even though you're adding energy. That's why it's latent heat, and the way you don't see it reflected as a change in temperature. Okay, that's why it's latent. You don't see it reflected as a change in temperature until you have that completed phase change. Okay, and again, this is called latent heat. There you go. Now, we have two equations. One of them is for fusion and vaporization. Now, this one, the one for fusion, that applies for freezing and also melting. And the only difference is this number, L sub F, this latent heat of fusion, will have a different sign when you're talking about freezing something, and we'll have the opposite sign when you talk about melting. Okay, so one will be positive, one will be negative. And then for latent heat or vaporization, now this one will be for boiling. No, sorry, not boiling. We're evaporating. Turning into a gas, and condensation. Okay, so now let's talk about the variables here. So as we know, Q is the heat, right? Energy, it's better we call it energy, heat energy. And units are joules, as usual. Let's try that again. Joules. M is for mass. Now, we can use kilograms or grams. We're allowed to use either or. But we need to make sure that our latent heat of fusion or vaporization, either one, has the units which will make sense with the mass. Okay, so let me explain. Now, L sub F is latent heat of fusion L sub V will be latent heat of vaporization Let's try it again. It's kind of silly. Maybe that's better. And the units will be, I'm going to write them, yeah, here's fine. Either kilojoules per kilogram or joules per gram. Now, if you're going to keep the mass in grams, then use the joules per gram. If you have kilograms, then use kilojoules per kilogram. Okay, so those are the units. And now I want to show you this graph. We like graphs in physics. This is a temperature versus energy or heat graph. And although, also, I've seen some tables with calories per gram and such, but we're probably not going to use those. Now the graph in your book had calories per gram, but that's okay, because I just want you to notice the shape and the way this graph is. And I think it illustrates why it's latent heat, like hidden heat. Now, notice this is temperature, right? Your y-axis is temperature, and your x-axis is the heat. This is calories per gram. Now, you have a very smooth, positive slope. Notice what happens at the freezing point in water, 0 degrees Celsius. You have no slope, zero slope, zero rate of change. But you still have energy, right? So this energy, notice, so let's go for red. I want you to notice this energy over here. You still have energy going into the system, but it's not changing the temperature. You have no change here, so you have no slope. This is where the latent heat happens. That's why it's important. Then also notice the length, right, here, the magnitude of this slope. It takes a lot of energy to boil water. I think you've seen it. Now, and it's also related to the mass, and I'll talk about it right now. I'll go back to the equation. It takes a lot of energy, right, to boil water. It doesn't take a lot of energy, I mean, in comparison to this, to freeze water, well, to melt water, and then it takes a lot of energy to get water and water vapor, and it says stream for some reason. Now, I got this from the book, okay? I think it says stream. I don't know if they meant that or steam. To be honest, I don't know. Maybe I'm wrong. Anyhow, then it takes a bit more than melting to make it into all water vapor or steam. And here again, we have no slope. This is again part of the latent heat of vaporization, this latent heat of fusion, latent heat of vaporization, no slope. We used to have energy going into the system, right? From here to here. There's energy. Now, going back to this, because I forgot. The mass. The mass is directly proportional to the heat required to undergo that change of phase. Yeah, there you go. I said it right. And it makes sense. Think about it. We're trying to boil a lot of water. It'll take a long time. You have a very small amount of water. It'll boil a lot quicker with less heat. It'll be in the stove for a lot less time. You can also see this graph in related to time, right? Because you're adding energy with time, with respect to time. So it takes a lot more time to boil water than it takes to melt ice. It takes a lot more time to boil water than to make boiling water into water vapor. So there you go. And now